Yeah. And actually, can someone nab that guy that just left? There was the video recorder.
Yeah. Yeah. Can I get you anything? Water? Water.
Okay, so that just went on. So my experience.
So that's to do anything special.
I don't. No, I don't think so. So
Just go to the mic.
yeah, I hope so. That's what we're trying to find out. So if that doesn't work, then we can figure. But
Donnie, do you want me to test this?
do yeah. If I emailed it to the links mailing list. So yeah, do try.
So Sashi went to go get it.
Excellent. Great. That's wonderful. Ben, also, so I'm gonna go ahead and just like get out of my other browser tabs just to like get Wi-Fi as good as possible. So if there's any emails from the links end of things, do you think you can handle it? Great.
Okay, so
I'm just not sure what the source would be.
oh, I think you need to log in and just go to like
I think so. Yeah, I think it's public. So
yeah, it's totally
great.
That's amazing.
I'm so glad. This is like one of the few times we've had.
Was it pretty easy?
It was pretty easy.
Oh, there's a big delay.
Yeah, there will be, unfortunately.
There's apparently people on the
Yeah, this is the one.
I guess I send it to YouTube and then back.
So switching my.
Yeah, there is. How bad is the delay? So like,
I think I'm looking at you from like 2 seconds ago.
oh, I just walked in front of it. Like 30
But there
seconds.
was another person just.
So how do we get to the detail?
Oh,
Oh boy. Okay. Is there something with when it got started or something? Do you think the delays somehow some? I don't know.
I think it's just a couple minutes late.
Why is it changing?
It might have been because did you set up a
No, we do. We did that.
Yeah. Sometimes it doesn't match up with what you have plugged in.
Yeah.
Oh,
So it's HTML.
wait, Steven's saying we should add people in the Google Hangouts view.
What's that?
Steve says we need to add people in the Google Hangouts view rather than use YouTube link for people to ask questions.
Yeah.
Feel free to add people then. So can you not do it on your end? Does it have to be me?
Wait, are you gonna try to ask questions?
Yeah.
It's a lot easier. Yeah.
We'll have to have yeah, that's a better idea.
I think maybe yeah. How about because I don't want to spend the whole talk.
Oh, yeah. Okay.
So one thing we can do is do that for now, and then
Yeah, at the end.
at the end I can change it to after we're done. I can change it to Hangouts, and they can ask if they want. Yeah, that's right.
Okay, so the projection is working. Is it? Will they see the screen on it?
What do you guys see on the screen? Does it look okay?
Oh, I guess you sent them the slides.
I did, yeah.
It's not that. I see.
Yeah. So.
So just for people's information, we are broadcasting the talk to University of Maryland to our East Coast folks. Because we're doing that on YouTube, I think it will be recorded. So if someone ends up wanting to refer to it, assuming Daniel's okay with this, we will, that will be available. And how are we? I guess I can be long-winded.
Sure.
So thanks everybody for attending. So today we're very pleased to have Daniel Laub visiting us. He'll be here all day. He's going to be giving a talk now. Actually, afterwards we're going to have a pizza lunch. So anybody who would like is welcome to join. We think that it's going to be in this room, but stay tuned. We haven't got that fully confirmed yet. If you would like to meet with Daniel in the afternoon, he'll mainly be around Links Labs. So feel free. I think Ben London here is kind of coordinating the schedule. You can talk with him. Daniel is an assistant professor at the University of Oregon, and he also has some Bay Area connections. So I guess he grew up in the Bay Area. So we're lucky to nab him on a visit home to come see us. Daniel's done a lot of really interesting work in learning in both graphical models and learning in relational graphical models. In particular, for his thesis, he did work on a lot of foundational work on Markov logic with Pedro Domingos and co. at University of Washington. Since he's been at University of Oregon, he's done some very interesting work on just learning in these settings and also adversarial learning. I don't know if you probably won't touch on that.
It's a completely separate hour-long presentation.
Yeah. No, we were discussing what to talk about, and there were a lot of different possibilities. But if people are interested in the adversarial setting, then they can probably ask him afterwards. In addition to this, he has some nice open source code, Libra, that's available for doing learning of these kinds of networks and different settings. So thank you for coming. Sorry it's raining today.
So just so I can aim this talk right, how many people have heard of some product networks before? How many people feel like you have a decent idea of what they are? Like maybe you've seen some tutorial or something like that. Okay. So there's a little bit of familiarity, so I'll go at medium speed. The start of this talk is really going to give some background on some product networks, sort of an introduction, and some of these slides are taken from a tutorial that I gave with Pedro Domingos, and so a number of these slides are actually created by Pedro, so I want to acknowledge that. And I figured that the structural learning stuff wouldn't really make any sense unless you had a pretty good idea of what these models are, what they're capable of, and why we care. So some of it will be sort of a background tutorial that will cover other people's work, such as the work of Foy Fung with Pedro Domingos. And then this second 2/3 or half of the talk, I'll cover some more recent results about how to actually go about learning structure with these models. So our overall high-level goal, which I think is probably shared by some people in this room and elsewhere, is we want to learn and reason with joint probabilistic models. The world is complicated and there's lots of unknowns, and all these unknowns are related to each other for the most part. And so there's lots of domains like natural language processing, vision, social networks, activity recognition, where we want to reason about a lot of related things jointly. And so we want to learn some kind of probabilistic model that will allow us to do that and capture the uncertainty and make good decisions. So there are a number of different ways to do this. The standard approach is to use some kind of graphical model, such as a Bayesian network or a Markov network, or some of these deep architectures like deep belief networks or deep restricted Boltzmann machines are basically hierarchical versions of Bayesian networks or Markov networks with lots of hidden nodes. And what's nice about graphical models is that you get a compact representation. So there's an exponential number of states to think about, but you break it down into small functions over a few variables, and you get a compact representation. But then when you actually want to answer a question, that's when things get really hard. Here's a simple earthquake alarm. How many people have seen this before? Okay, that's what I thought. You try to answer a question, like the probability for a given alarm, you need to sum out earthquake. With 3 variables, it's no problem. With 10,000 variables, it's a big problem. Even with 100 variables, it can be a big problem because it goes exponentially in the tree width of the graph. So exponential inference is sad. Approximate inference algorithms aren't always good enough. So what's an alternative? An alternative is, instead of learning a model or building a model where you can't reliably get good answers out of it, you could focus on learning a model where you can reliably get good answers out of it. So in this talk, I'm going to focus on how to learn tractable models where you can do exact inference efficiently. And the reason why people haven't been doing this all along is that restricting it to be tractable is potentially a significant restriction. So if in the general case it takes exponential time and you're only looking at the case where you can do things efficiently, this necessarily means you're excluding some models. And if those models are the right ones, then you might be nervous about doing this. So this can be the case with low tree width models or some simple mixture models. Given the data, we'd like to find the most expressive, most powerful probabilistic model we can in terms of fitting the data that's still tractable. And then there's this, so then there are a couple of questions. One is, how can we do this? And then the other question, which is an empirical one, is, when we do this, how well can we fit the data? Is tractability a big restriction or not a big restriction in terms of getting accurate probabilistic models? So there are many tractable probabilistic models, some that I know people here work on. But I'm going to focus on some product networks, which are a nice class of models that capture a lot of the other tractable classes, not Higgs-Boson marker random fields, but at least many others. And after
We'll
some...
fix that sometime later.
Okay, we'll come up with the right generalizations. Higgs-Boson some product networks. Okay, look forward to that. So I'll give some background on some product networks, and then I'll talk about 2 different ways to go about doing structured learning. Well, actually, 3 different ways, 2 different approaches, and then how to combine them. So I'll talk a bit about how you can take standard methods for learning graphical models, standard graphical model structure search, and extend it to learn tractable probabilistic models without exactly restricting your representational capability in any way. At least not restricting it a priori. And then I'll talk about related work by Rob Gens and Pedro Domingos on learning hierarchical mixtures to get some product network structure. And these 2 approaches are going to learn completely different structures and represent interactions among the variables in completely different ways. And this is what happens when you have a really flexible model class like some product networks. There's many ways to do things and many choices to make and a huge search space. So since these are doing completely separate things pretty much, maybe we could combine them. And this is what we did in our most recent ICML paper that came out this summer. We showed how you can combine these 2 ideas and you actually end up with much more accurate models by capturing both kinds of structure in the data. And then I'll show you that this is often more accurate than Bayesian networks while also being tractable. And I think that's exciting. Okay, so now some medium-paced backgrounds on some product networks for those who aren't familiar or would like a refresher. So we're going to start with the definition of an efficiently summable function. We'll say that a function is efficiently summable if and only if you can compute a sum over any subset of its scope in polynomial time. So in general, if you're thinking about a function like a probability distribution, if you have 100 variables and you want to compute you want to sum out 50 of them, that generally takes exponential time, but we don't want it to take exponential time. We want it to take polynomial time in the cardinality of the subset. So here's one way to describe a way to come up with efficiently summable functions. That's a sort of recursive definition that will naturally lead to some product networks. So basically, if you have two efficiently summable functions that have the same scope, then that sum is efficiently summable because you can do the sum separately. So if you have a sum of two functions and they're both over the same scope, because addition is associative and commutative, you can just do the sum separately, and so you can do the overall sum efficiently. And this is basically what you get with the mixture model. And then the second condition is if you have a product of summable functions with disjoint scope, so here we have a sum over the sets of variables A and the set B. It's a little blurry, sorry about that. And you have some function f of A and a separate function g of B. Well, then based on the distributive law, you can split this sum into the product of two separate sums. And if you can do this one efficiently and this one efficiently, then it's easy to compute their product. So this gives us a way to sort of recursively define more and more complicated functions that are efficiently summable.
Scope is different than arguments?
Scope is the, yes, scope is the arguments. So the sets of variables that are the arguments, yes. Okay, so let's look at how we apply this to come up with sum product networks. A univariate distribution is a sum product network because we assume that these are generally efficiently summable. Maybe you can come up with a really evil univariate distribution, but most of the time they're efficiently summable. And often we're just looking at multinomials and considering the discrete case. And for most of this talk, I'll be focusing on the discrete case. It's hard to come up with a difficult to compute multinomial unless you put, like, I don't know, busy beaver function in the denominator or something weird like that. So this is generally efficiently summable. Now, if you have a product of SPNs over disjoint variables, then that invokes the second law of the second condition for efficiently summable functions. And this is what you have when you have a product of independent probability distributions, like P of X times P of Y. And you know, when things are independent, that usually makes inference easier. So this makes sense, a product of SPNs over disjoint variables. Or you can have a sum of SPNs over the same variables. So here we have a sum of one SPN over X and Y and another SPN over X and Y. And we'll do a weighted sum. And you can view this as summing out a mixture variable, if you like mixture models. So this is effectively a mixture of two distributions, one and then another one. And I just want to mention, it's tempting to think of the product as introducing independencies. But note that in this model, X is not independent of Y. Because once you sum over the two submodels, you do get interactions between X and Y. So within each component, X is independent of Y, but just like with the 90-phase mixture model, even though in each component, all of the variables are independent, when you look at the overall distribution, there can be arbitrarily complicated dependencies among all the variables. So this is still a very flexible, very powerful representation. We're not making big independency assumptions here. And then you can apply this over and over again in all kinds of different ways. And you can reuse one SPN in multiple contexts to come up with all kinds of interesting, complicated distributions that are more and more complicated. And this is the kind of structure we're going to be searching over. So naturally, we have potentially a very difficult structure learning problem. It's actually lower level than looking for a graphical model. With a graphical model, you're often looking for edges or maybe a little more detailed something about the features or potential functions or conditional probability distributions. But here, there's actually a lot more flexibility and many different ways to represent the same distribution. So it's potentially challenging. We're going to need some kind of heuristic to search through this space. So here's an example application, which is why people started getting excited about SPNs and why people care about SPNs. This got the Best Paper Award in UAI 2011, work by Hoy Fung Kuhn and Peter Domingos. And they showed that for applications like image completion, you're learning basically a distribution over images of faces. And then conditioned on Here it's conditioning on the right half of the face. You want to predict the pixels for the left half of the face. And as you can see, it's able to do things like a pretty good guess about how to complete that beard, some sort of vague guess about how to complete those glasses. Not perfect, but it's doing a decent job. And when they compared to deep leaf networks and deep wolfram machines and other methods, they had significantly lower error, but it was also orders of magnitude faster. So here you're seeing tractable models that are giving you more accurate results than the intractable model. And so this is exciting. Here they were using a particular structure that was hand engineered for this problem and was designed to exploit the specific 2D structure of these images. And for some of what I'm going to talk about later, we don't necessarily have that 2D structure. So the architecture that they use was you want a distribution over the whole image, and you can break that into something. If it's an n by n image, there's something like n choose 2 times n choose 2, so approximately n to the 4th possible regions in there. And so you'll have a set of different distributions for each region. Different, you can think of them as like different mixture components that could represent possible distributions given some other context. And you combine those basically in all possible ways. So you think of all the ways you could split the image by slicing it one way or another. And then each of those pieces could be sliced one way or another. But you're going to have the same region show up as a sub-region of multiple super-regions. And so in that way, you're able to reuse a lot of the information and have tight parameters and be able to actually learn this thing from a reasonable amount of data. And so you have this kind of hierarchical distribution that's also reusing a lot of components. And this worked very well for image applications. Another way you can think about some product networks. Once again, these early slides are by Pedro, so I can't take credit for this, but I think is a really good explanation here. If you're trying to gain some intuition about what SPN could represent beyond just thinking about addition and multiplication, one way of thinking about it is you have a distribution over a whole image. You can break that image up into parts, and then each part has a distribution that could be roughly independent. So you have the street, you have the person riding the bicycle, you have part of a car or SUV or something. You have all these different pieces of the image. And then for each piece of the image, each part, you have many different possible types. So this could be a person riding a bike taxi or a person walking on the street, or there's many different things that could be right here in the image. And in this case, it happens to be a person riding a bike taxi. Well, that person riding a bike taxi can be decomposed into separate parts, the person and the bike taxi. And this person can could be one of several types. I guess it could be a lamp instead, depending on what that looked like. So you get the basic idea that, and this is something that people have done somewhat similar work with and/or graphs. You have this decomposition where you're splitting things into multiple pieces, and then each piece can have multiple types, but then each one of those sub-objects of some type can have itself has multiple pieces with multiple types. And then at some low levels, a distribution like a distribution of what a person looks like, that could end up being reused in multiple contexts. It could be like a person in a car, or a person on the left or on the right, or things like that. And so some product networks are naturally able to capture this kind of stuff. Another way to gain some intuition about some product networks is to think back about what you know about graphical models and those kinds of probability distributions, and look at how we can construct some really simple sum product networks for really simple distributions. And then we'll get more complicated from there. So suppose you want to represent a product of marginals. It doesn't get much simpler than that. So here you have a Bayesian network with 0 edges, just a marginal distribution over x, an independent distribution over y, and independent distribution over z. You pretty much never want to use that network except maybe as a strawman baseline. How can you represent this? Okay, it's just a product of a distribution over x and y and z. Okay, so pretty simple so far. It's encouraging that we can at least represent this. That's a good starting point. So how about a naive Bayes mixture model for the case of binary random variables? This is often called a mixture of Bernoullis. So in a Bayesian network, you could represent this with a hidden or latent variable that represents the mixture component. And this is unobserved in the data, but you can learn with EM or something. And then you have, once again, your 3 random variables here. And I'm just showing this with 2 mixture components because it fits on the slide better. But here we would have a sum over 2 different mixture components. One is a product over x, y, z, and the other is also a product over distributions over x, y, z. But these can be different distributions, and so you end up with a more complicated distribution. And then if we had, 10 different states of this hidden variable, we would have to have 10 different products to sum over with weights that we probably want these to sum to 1, or we have to renormalize later. Any questions so far? Yes.
Can some product networks represent the XOR function?
Sure. I can tell you how to do that right here. So you just have a probability of 1 for x and 0 for y equaling 1, and a probability of 0 and 1 for them equaling 1 over here. And then you have a deterministic distribution where x is 1 and y is 0, and another one where x is 0 and y is 1. And you can make sure of those, yeah, easy to do. Okay, now let's go a little more complicated. How about a low truth graphical model? I'll just show a chain among 3 variables. So this is a tree root of 1. And so x is a parent of y is a parent of z. And so as a Bayesian network, you'd have a product of p of x, p of y given x, p of z given y. And what's important and interesting here is that z does not depend directly on x. So if you condition on y, then z will not depend on x anymore. You have x and y, x and z independent given y. So we should be able to get some sort of reuse in the structure here too. So again, it's getting a little more complicated because an SPN is a lower level representation than a Bayesian network. It's sort of representing all the computations you have to do in order to compute the answer by running something like variable elimination. So here we have basically a sum over the different values of x, and I have a deterministic distribution here. Here I have a probability of 1 for x equals 0, a probability of 1 for x equals 1. And so this here, just this top, is basically capturing p of x. And then next I have, for each state of x, I have a distribution over y. So for this state of x, I have one distribution over y represented by this summation over these 2 states of y. And here I have a different distribution over y. So this is what's really capturing p of y given x, because I have different distributions there. And then I have, again, different distributions for p of z given y. But note that with these crossed lines, there is reuse of the distribution over z that does not depend on x. So if you added an arc from x to z, so that z depended on x and y, then you have something that was more like a tree, where you would have 4 different pieces there. A little more complicated, but does the basic idea make sense?
By the accident in this slide, you're actually representing the same distribution for y on both tracks. Because for 1 plus, you have 0.9 and 0.1, and then you have 0.9, and then another 0.1.
Yes, so that's
just by accident.
Yes, by accident.
So it does seem to me that some product networks are kind of like skipping the Bayesian network and going straight to like the variable elimination. And so to me, like this is like one possible criticism is like you kind of skip the hard bit, which is like picking the correct elimination ordering versus the NP-hard problem. You gave that to the user and said, hey, give me what the elimination ordering would have been. And then now I can just do everything, the easy bit, and that's my sum product network.
Right, so well, there's several ways to think about it. One is, yes, the learning problem is harder because the learning problem is also sort of choosing how to do inference at the same time. One way I like to think about this is, if you're doing structured learning, you're trying to learn an inference representation.
Yeah. So I think like structured learning seems like the whole game here, because if I just gave you the sum product network that was like avoiding the whole problem with picking the elimination ordering and putting that on the user, but then if you do structured learning, then now actually you still have to do that.
Yes.
So you still have to do the hard bit.
It's also worth keeping in mind, though, that there's many things you can represent with some product networks that you can't easily encode as a Bayesian network. So if you just think about a naive Bayes mixture model, If you tried to represent the naive-Bayes mixture model without the hidden unit, then you'd have just an ugly clique there. Well, if you tried to represent this distribution, what you have is a really complicated set of hidden variables where, conditioned on a certain set of the hidden variables, you always have a tree distribution over the other hidden variables, but it's not easy to represent as a Bayesian network. So as you use more and more of these mixtures with non-deterministic distributions, then things look less and less like a Bayesian network, and they look more and more like a really complicated mixture model that's still tractable. So when you're thinking about Bayesian networks, your intuition is correct, but it's important to also think beyond Bayesian networks to what else these can represent, how we can go about them. Yes.
Yeah, so that brings up a question we'll probably get to later on, but I bring it up. So let's say I have an algorithm that outputs an SPN. Is there any way to decode that SPN and say, oh, this is actually equivalent to some directed or undirected graphical model?
That depends on how you learn the SPN. So I'll show you some methods that actually, they learn an SPN that's equivalent to a Bayesian network or a Markov network. And then you definitely know the equivalent structure. There's other cases where you have this hierarchical mixture model that's not easy to express as a Bayesian network. But I mean, in the limit, you can always represent it as a big clique with an exponentially large table, right? So, trivially, yes, sometimes you can do something better than that. Okay. Onward. Okay. So as I was saying, there's lots of graphical models and lots of sum product networks. And sum product networks are, if you think of the standard tractable models, they're generally special cases of graphical models, and sum product networks can represent most of those, like mixture models and low tree graphical models. But they can also represent some things that are graphical models, but not the standard tractable model classes people have looked at as much, and many models that you can't easily write down as a Bayesian network, or will not be able to write it down. But the big advantage of working in this class is now you have polynomial time exact inference. And this is going to be good if you want to actually learn parameters, especially with missing data, or if you want to be able to get answers ever.
But you're saying that those things aren't graphical models, or it's hard to represent graphical models?
In the limit, any discrete probability distribution would be a graphical model, but you'd be throwing away the structure. So,
They kind of represent like this kind of diagram. What is the thing that defines what's in it?
right. So this is not a very precise Venn diagram. If you allow your sum product networks to be exponentially large, then you can represent any graphical model with the sum product network, because you just take the junction tree and code that as a sum product network, and you have an exponentially large sum product network, but you can do it. And similarly, if you have a sum product network that's a discrete distribution, you can encode it as a graphical model by just having exponentially large conditional probability distributions, and you can encode any discrete probability distribution that way. So if you allow exponentially large models, then I guess these are the same for discrete distributions. But if you think about reasonably sized fits in the memory models, then there's some non-overlap.
But can we view it as just a direct graphical model with like hidden nodes at each of those products and sum nodes?
Not easily, because you have context-specific independence that makes it really complicated. So, there's no there's a whiteboard here. There's a bit of whiteboard here. So suppose I have a sum over. Here I have p of x, y times p of z. And here I have p of x times p of y, z. So in both cases, the scope of these nodes is p of x, y, z, p of x, y, z. So I can definitely compute the sum, let's say 24 arbitrarily. But I have different independencies here. So even if we're doing this as some latent variable, you have context-specific independence where when H is, let's say this is 0. When H is 0, then Z is independent from X and Y, and when H is 1, X is independent from Y and Z. But as you have lots and lots and lots of sum nodes, the context-specific independencies become extremely complicated to where they would be really messy to write down.
So I really kind of think of it as like a generative process with kind of structure.
You could think of it, can you model as a generative process? Yes, you could. Starting at the root, randomly pick one of the children, and then recurse to randomly chosen one of the children of the sum node and all of the children of the product node. So yes, you could use it as a generative model.
But then in that case, you could write that down as like a Bayesian network, right? You write down that generative process as like a Bayesian network.
The challenge with doing that comes when you have one hidden node that can appear in many different contexts. And then when you want to, so then your conditional distribution for this hidden variable says that its probability distribution depends on so many other things that the representation for that can become ugly.
Okay.
So maybe you can find a way to do it. I don't know that I'd recommend it, but if you come up with something interesting, then
You're just going to think about it.
yes.
So one of the things you sort of mentioned is how many different discrete distributions are representable by these networks. And it seems obvious to me that in fact any discrete distribution is representable by such a network. So my question is it known whether or not every continuous distribution is representable by some product network?
I don't know how you define the set of all continuous probability distributions. I have not given that thought. I might need to take a class of measure theory first.
Thank you.
Okay, so now I want to briefly talk about a closely related representation, arithmetic circuits. So these were used by Anand Darwish. He had a nice paper in Journal of ACM in 2003, and then he had some nice follow-up work on how you compile graphical models into this low-level inference representation for doing exact inference. And what's nice about arithmetic circuits is when you do this compilation, you're able to take advantage of structure like determinism and context-specific independence to get something that's more compact than a junction tree. And an SPN and an arithmetic circuit are basically equivalent. So they both have product nodes. In an SPN, you have weighted sum nodes. In an arithmetic circuit, you have unweighted sum nodes. But you can make the sum nodes weighted by multiplying in additional parameter nodes. So in the SPN, you also have univariate distribution versus indicator variables, which are like deterministic distributions. So I can go back and forth between these representations. And for part of my talk, it'll be more convenient to work with arithmetic circuits, which are slightly lower level than SPNs. And for some of it, it'll be more convenient to think about SPNs. But these are basically equivalent. But back, a decade ago, arithmetic circuits were mainly used for inference. You take your distribution, compile it to an arithmetic circuit. Now you can do inference with linear time in the size of the circuit. SPNs were proposed more as a representation, and so they're equivalent, but they have slightly different histories and connotations. But you can convert back and forth between them with no exponential flow. Okay. And so here, this piece is representing P of X as a sum of some probability for X and some probability for not X, and so it's easy to convert. Okay. And then you can compute marginals in linear time by, if you want to sum out Y, then you just set this distribution over Y to 1 because you're adding up all the values of it, and then you go up, and you have some value at the root. And to get the probability of X0, you look at the value for X equals 0 in each of these roots. And then you can also compute conditional probabilities, and you can approximate map states and do all kinds of things. Good so far? Okay. So now let's look at the tricky problem of structural learning in a representation that's much more expressive than graphical models, and therefore this has a much larger search space, and structural learning graphical models is hard to begin with. So, as I said before, you're going to need some way of searching through this really large space. If you just blindly go in and say, well, let's look at all possible ways I could put together addition and multiplication operations, you're probably going to get very stuck and very confused very quickly. So another approach is to say, let's take graphical model structural learning algorithms and somehow use them as a learning bias to learn some product networks, or alternately, use some product networks as a learning bias for learning tractable graphical models. Okay, let me show you what I mean. So I'm going to start by taking a standard method for learning Bayesian networks with tree structure conditional probability distributions, and then show how we upgrade that to learn compact sum product networks. So we're going to learn a Bayesian network, which is some distribution represented as conditional probability distributions. And we're going to use tree structure conditional probability distributions, which means that we have some context-specific independence. So here I have P of D given BC. In general, you might have 4 independent parameters or more depending on the number of values each of these can take on. But for this particular distribution here, if I use a tree to represent it, I can have a probability of 0.2 when B is true, and I can, and when B is false, I'll also test C, and I'll either have a probability of 0.5 or 0.7. So what this means is that when B is true, D does not directly depend on the value of C at all. So D is has context-specific independence from C given B is true. And this means that now I could have, D could have like 20 parents, and I don't have to represent all of those combinations of values as long as I have some kind of tree that tests the combinations that I care about. And the standard way to go about learning this is you start with an empty network, and then you have a really boring decision tree with just a single leaf for each node. And then you're going to split these decision trees greedily by adding whichever split helps the log likelihood the most, and also enforcing acyclicity so that you have a validation node. Just a simple greedy approach. It works pretty well, gives you pretty good probability distributions. But of course, the models you learn, doing inference in them is generally going to be harder. So we'd like to do this, but actually end up with a tractable probabilistic model. So how can we do this? Well, you could just learn a bunch of Bayesian networks and try to compile them into some product networks or arithmetic circuits. But most of the time, it will just blow up and it won't work. So instead of just trying and failing and being sad, we'll use the size of the arithmetic circuit representation as a penalty while learning the Bayesian network. So if a Bayesian network has a small arithmetic circuit, that means we can do inference efficiently. That's good. If it does not have a small representation, that's bad. We want to avoid those. So this is just going to bias our search through the structure space. It's the same structure space as before in terms of the Bayesian networks, but now we're going to bias it towards tractable models. So how can we do this? We will, instead of using the representation complexity as a regularizer, we'll use the inference complexity. So a standard approach would be look at the log likelihood of the data given the model, and then penalize it with some function of the number of parameters. And instead, we're going to penalize it with some function of the circuit size. So we're going to use this as our bias or regularizer. How do we do this search? So we could just recompile with every single candidate structure. That would be extremely expensive. So instead, we're just going to maintain an arithmetic circuit or SPN that's equivalent to the Bayesian network. And as we consider modifying the Bayesian network, look at the same modification in the arithmetic circuit, or so that we always have equivalent models. So just to give you a brief idea of what this looks like, here we have, as part of some giant arithmetic circuit, there's some distribution over A here. It has some parameters, and this is representing some distribution over A. And we want to condition A on B. And so there's some node up here it's a product of something involving a distribution over A and something involving a distribution over B. And now we want A to depend on B. And in order to do this, what we need to do is we need to, right, so this is a distribution over A and something, this is a distribution over B and something. And we want to make it no longer independent so that A can depend on B here. So how do we do this? Well, we want to have a distribution of A given B true and another distribution of A given B is false. And so what we do is we have a sum over the two different possible values of B. And now here we have the distribution over A and other variables given B true, given B false. And similarly, we have a distribution over B and the other variables when B is true and false. And so we're copying portions of the network, in the worst case, doubling in size, but hopefully not most of the time. Yes?
So do you create the initial SPN or the circuit? So you get some sort of
no, so the initial circuit is a product of marginals. Your elimination order it doesn't matter. Then.
Oh, okay.
Yeah.
It's always doing splitting everything.
Right. Merging would be complicated.
But could you get a different SPN by like some other equivalent elimination ordering to a Bayesian network?
So the yes. So the mapping from Bayesian network to SPN is not unique. Right? And in fact, it's only going to be NP hard or worse to get the optimal one because just getting the minimum tree width is NP hard.
Right, agreed. But then does that make this like your definition of your regularizer kind of not well defined because if it, like you didn't know which of those you should have picked?
It's well defined by construction. So I use the current arithmetic circuit and I use a sound way of transforming it to incorporate a structure move. And while that's not the only way,
so I guess the regularizer penalizes the pair of Bayesian network and arithmetic circuit.
Yes.
It doesn't penalize the Bayesian network by itself.
Right? Sure, that's a reasonable way of thinking about it. So the goal is actually to learn tractable probabilistic model. And the Bayesian network is useful as a guide through this huge space to find one that we know works well, because we know that learning Bayesian networks works kind of okay in a lot of domains. And so it's a good guide for how to go about learning something like the arithmetic circuit. And note, this is not a local operation. This is a copy giant chunks of the arithmetic circuit kind of operation. So if you're just thinking about local operation in the arithmetic circuit, that would be too low level to do things like this. Whereas it is local operation in the Bayesian network. So that gives us a way of figuring out good things to do in the arithmetic circuit.
I guess if you're thinking of it as really penalizing the SPN rather than penalizing the Bayesian, then
yes,
it would probably be more defined.
Yes, that works. Okay. So we start with an initial product of marginals and an initial set of possible splits in the Bayesian network, and then we're just going to iterate, considering each possible split of a decision tree leaf. Try applying it, scoring it, undo, and get the best one. So this is just really hill climbing style structure learning. And there's some additional details here and in the paper about exactly how to figure out which portion of the circuit to copy to make sure you get something valid. But I'm going to move on because I've already taken a lot of time and I want to leave some time for the rest of the topic. So we then extended this to handle Markov networks. So if you want to do search through a space of possible Markov networks, one way to do it is if you're trying to learn a lot of feature functions, and you can start with the feature functions you have. So if you have a feature function A and B, then you might consider A and B and C, A and B and D, etc. So once again, you have a space of possible structure operations to consider. And you're going to score them and add the best one. And so once again, you can do something similar where you use the size of the arithmetic circuit, SPN, as a penalty. And this means that you can do exact optimization of likelihood. And you get slightly better accuracy, although only slightly, because in both cases you're constrained to have a compact arithmetic circuit. So you end up with, once again, you're copying chunks of the circuit. But now as you're extending a feature with some parameter theta to be two extended features, if a feature is a super, longer and therefore more constrained, and each one also needs to include the original parameter as well as the new one. So this works for Markov networks as well as for Bayesian networks. Okay. So next I'd like to talk about a completely different way to go about learning sum product networks. That's going to look at basically local modification in the sum product network rather than in some other kind of structure. And it's really going to use these the possibility of SPNs to create mixtures. So previously, this was learning something equivalent to a graphical model with no hidden variables at all. But one of the cool things about some product networks is you can have all these hidden variables connected in really complicated ways that might not correspond to any easily representable graphical model at all. So clearly by doing this, I'm ignoring a lot of possible interesting SPN structures that might be very good. And I'd like to capture some of those. So Rob Gens and Peter Domingos came out with something completely different a year ago, where they're going to, in a top-down way, recursively create sum nodes and product nodes by doing two different kinds of clustering. So you have your original training set, which you can think of as a matrix where you have variables and instances. And if you find a group of variables that is approximately independent from another group of variables, then you can return a product node. Or if you don't have any independence, then you can cluster the instances to be similar groups of instances, and there you have a mixture of the different clusters of instances. So here you're clustering the instances, here you're partitioning the variables, and you just recurse and you get this tree structure that has lots of these sort of implicit hidden variables. And you keep going down until you get to univariate distributions, and then you stop. So completely different structure. And then you might want to ask, when would I prefer one or the other? So you can easily come up with cases where mixtures are better. So like if the probability of each of my random variables is 0.9 in one component and 0.1 in the other component, it's trivial to represent that as a mixture of Bernoulli's. But with no hidden variables, you'll need a full cube, and it's going to be really hard. What about when are direct interactions better? Well, if you think about something like a grid structured Markov-Random field, each of these nodes has a small number of pairwise interactions that are relatively easy to detect from fully observable data, because you can estimate sort of each one more or less independently. But if you try to represent this as a mixture, well, you want to have a mixture that makes other groups of variables independent. So if you want to pick a group of variables where you can have a mixture over different possibilities and make other groups independent, you can have a mixture over all 64 states of these variables, and given one of those 64 mixture components, these variables are independent from those, so you can do it, but it's going to be really hard to learn because you're going to generally require lots of mixture components, and it's just going to be less efficient to do well. So if you have lots of local interactions that are direct interactions among the variables, you want something like a Markov network or a Bayesian network to capture that. But if you have these, if you have some cluster patterns in the data, then you want to have something with hidden nodes for representing that. Yes.
So like high level, if you use computer vision, you use the local interactions, and if you're doing, what would be the other thing? What would be the case where you want to use mixtures?
I think you want to use both.
Okay.
Because I think both of these patterns show up in many data sets. I think it's common that you have some clustering, but the clustering doesn't quite capture it, and you want to have some direct interactions as well. So let me show you how we learn this. So comparing and contrasting these different approaches, in both cases we're doing some kind of media structure search, but in one case we're doing local changes to the SPN, and the other case we're doing local changes to a Bayesian network, which are big global changes to the SPN. And then these interactions are represented either directly through features or indirectly through mixtures. And so these are capturing different things. And I tend to actually want to do both. So let me show you a really simple way to do both that works really, really well. So we're going to try to learn both the indirect and direct variable interactions. So how can we do this? Well, we can start by learning a tractable Markov network, using the Markov network approach to learning an SPN. And then we can, so there's our initial model, some tractable Markov network. And then we can also try clustering variables and instances to create a product of sums. And then learn tractable Markov network that we use here. So this is like doing one step of learn SPN, but instead of recursing all the way, we stop and learn more complicated models for the leaf distributions. And then whichever one of these is better, we choose that. And then we recurse. So if this one's better, then we recurse on each of these and consider replacing them with basically another step of learn SPN. So maybe we try taking this model and replacing it with a submodel. So let me show you here. Here's another leaf. We try to take the leaves and compare them to basically again one step of learn SPN, all the instances used for that. And we end up with another distribution. We compare the log likelihoods, and if it's better, then we're just going to swap that in and keep going, looking at replacing leads with more mixtures and partitions. So now we clearly have a generalization of both the learn SPN by against Domingos and the ACMN algorithm, because it can represent both. But now we can do combinations where we have both indirect interactions and direct interactions. And I'll show you how well it works in some experiments. So we evaluated this on 20 data sets. There were actually also data sets used by Vincent and Domingos. And these range with 16 to almost 1,600 variables. So we tried the obvious baselines of the simplification of this algorithm, learn SPN and ACMN. We also tried mixture of trees, latent tree model, and we tried learning intractable Bayesian networks with the decision tree CPDs. So all of these are going to be tractable models. This will generally be intractable. And we'll look at log likelihood and also conditional marginal log likelihood. I think most of these results I'll show you are just log likelihood. So what do we see? Uh-oh, it's a giant table, scary. So let me use colors to highlight the differences. So here is ID-SPN, the new method that I claim is neat. And if you compare it to learn SPN, then actually it's better on 20 out of 20 data sets. And it passed a basic statistical significance test on, what was it, 12, 14, something like that. Of them, I think it's on a later slide. If you compare to ACMN, it passes statistical significance test of being better on most data sets, but there's a few where it is a little bit worse.
So we're comparing to the left-hand column?
Yes, yes. So ID-SPN here, sorted by number of variables. So few variables, many variables. And if you look at mixture of trees, it's almost always better, except for this one case where it does worse. It's pretty much always better than the tree model. And this is interesting. If you compare it to an intractable Bayesian network, these are the distributions that we might be sad we can't learn. Except now we're not too sad because we're doing better most of the time. And this is just log likelihood. If you actually try to get answers out of these Bayesian networks, you're going to get bad answers because inference is hard. Well, for complex queries, you'll get bad answers. For simple queries, you might be okay with your sampling or the propagation. You might be fine. Lots of evidence, simple queries. But in general, you have no guarantees on how terrible these results could be when you run inference. But most of the time, the log likelihood is better for our method than WinMine anyway. There's a few data sets where the Bayesian network is a little bit better. But this is interesting because it suggests that learning a tractable model doesn't have to be worse than learning an intractable model. And I think really what's going on here is that WinMine is only capturing the direct intractables among the variables. So it's not learning any kind of mixtures, and it's therefore ignoring that useful kind of structure that's present in many data sets. And because of that, even though it has the ability to learn intractable models, which is more of a bug than a feature, I think, it's doing worse because the combination of direct and indirect interactions is powerful, because you expect that these two kinds of patterns are going to show up in many data sets, not just one or the other. Okay, so if you just compare number of wins and losses, ID-SPN is usually better 13 out of 20 times on WinMine. These are the ones that pass the statistical significance test. So I'm cautious about saying significant because that number, that language gets abused so many times in scientific papers, but pass the statistical significance test. So it's consistently better than the base methods, it's better than other tracking models, and it's usually better than intractable models. So I think that's exciting. Okay, so for conditional marginal log likelihood, if you look at how long does it take to run inference, like running good sampling for a short time, then as you have more non-evidence variables, win-mine is going to be slower. These methods are pretty fast, but they become slower as you have larger and larger and larger SPNs. And we find that it's significantly more accurate than win-mine on 95 out of 100 data set evidence configuration. So win-mine does worse on log likelihood most of the time, and it does even worse when you actually ask it to answer questions. So I hope I've convinced you that some protocols are at least interesting and worthy of study. And intractable models, they overcome what I think is one of the biggest limitations to really using graphical models effectively, or probabilistic models in general. Intractable inference, it makes learning hard, it makes using them hard. Sometimes you can get it to work, but it means that you're never sure if it's going to break, because you apply it to a new domain and you just get horrible results because you have NP-hard problems. But the tractable models avoid that. And I've shown you two different ways for learning SPN structure, and then a third way where we combine those to do even better. And I've also suggested that tractable models don't have to be less accurate than intractable models. In many cases, a tractable model can do a pretty good job of capturing the interactions you care about in the distribution. So you can use intractable models if necessary, or preferable, or there are good reasons to use them sometimes. But in many cases, tractable model will do, so they're definitely worth considering. And what we're working on next is trying to learn structure for the discriminative case. But there's, as you see, out of the vast possible space of structures and structure learning algorithms, we're only just sort of beginning to look at what can be done. And so there's potentially a lot of opportunities to do better. If you want code, there's code. Okay, that's it. Questions?
So like the previous slide with the free table, that was negative first. That was one negative. That's the training data. Test data. Oh, that was the test data. Oh, okay. Okay.
Tangential kind of question. So your original method that you described was optimizing this generalized log likelihood. Just the Jansen Dominguez paper does that. It's very intuitive, but does it also optimize like a very clearly defined vector function?
It's also optimizing log likelihood. Okay,
that's good, because then if you combine the two, then they should still also be optimizing log likelihood or some generalized.
And actually, to be fair, there are several methods for learning some product neural structures that I have not talked about. So I actually don't want to convince you that this is the only ways to learn. There's a few papers for learning sort of top-down or bottom-up. They're mostly focused on learning structures similar to the Puna-Dominguez structure, where you have that hierarchical breaking down into parts and subparts, which is really good for images. And they relied on being able to do clustering in certain ways that I don't think would generalize to other discrete data sets in general. But you should be aware that there are other methods of doing this, where you do some clustering in order to figure out basically what the regions are, and then you assemble the regions in a hierarchy similar to the region, so that there is other work that I have not discussed with you yet.
Actually, Daniel, I'm curious, is there a way that the links guys can ask questions, or no?
So I think we're gonna maybe afterwards I can put them on Hangouts or something so that you can actually interface with them, because I think right now it's just broadcasting. I don't think they're going to be able to chime in.
Okay, so actually, other local questions?
Well,
I'm curious. Oh,
Go ahead.
okay. I was curious about like statistical significance because in those examples, how was it measured?
So I believe that was a paired t-test, two-tailed, less than 0.05. So that the null hypothesis there is something like the probability of getting that difference on that data set with those algorithms. If you want, though, here's another statistical significance test that's easy to do. What is the probability that ID-SPN beats LearnSPN on 20 out of 20 data sets if on a randomly chosen data set from the same distribution, key qualification there. So if you randomly choose a data set so if LearnSPN is better on average than ID-SPN or their equivalent on some distribution of data sets, then what's the probability that we win 20 out of 20 times? That's going to be something like 1/2 to the 20th, or if one may be two-sided, 1/2 to the 19th.
So is it a sign test or something like that?
Yeah, so you can just do, so this is for individual pairwise differences, but the probability of being better on 20 out of 20 is, I think, a sign that you will get at least slightly better results with ID-SPN than LearnSPN almost all the time. But sometimes you'll do worse than other methods. But still, it looks, I think it looks pretty good. At least on this distribution.
You could do a test on that, like I think the sign test, I think those are like, kind of you got some pluses and some minuses. Is it better because there's more pluses than minuses?
Yeah.
You could actually do that test. I don't know if you did it.
Well, so I believe the sign test is easy to do here because really the probability of getting that is 1/2.
That's definitely,
I guess this would be 1/2 to the 20th times 22's 3, something like that. Yes.
I was just wondering, since you guys have worked on this and everything, have you tried it on any bigger data sets?
Bigger in which way?
More variables.
Well, we've gone up to 1,600 variables, which I think is at least a medium size. There are definitely larger data sets. But no, 1,600 is the largest we've tried. What we'd like to try sometime soon is actually looking at how it performs on some image data sets, where people are all excited about deep learning and where SPNs have done well on some of them in the past, and see how it compares there. And we don't know exactly how well we'll do on like MNIST or base completion or other things like that. But that'll be interesting to see. So hoping later on we'll look at that sometime soon. So many things to do. Yes.
Do you find that this scales better with size of data or with dimensionality? And is either one of those like a big problem for this algorithm?
So scalability. The current implementation is pretty slow, but could be made faster because when you're doing any kind of research, you can always just be more heuristic and less greedy by considering fewer things. So if you're considering all possible ways to extend something, then the number of possible search operations is going to grow linearly with the number of variables, which means, well, the number of ways to extend a single feature grows linearly, which means the total number of options grows quadratically, and then you might actually have more iterations, so it could even go cubically. So as you increase the number of variables, things definitely get slower, and you can come up with some kind of clustering or other way of restricting the search to make it faster. I mean, you can trade off sort of accuracy and efficiency there. As you increase the number of examples, it's just going to, running time will increase linearly with that because you're just iterating through and scoring those examples. Unless increasing the number of examples increases the complexity of the learned model, in which case there could be, it could be not linear, but
so you can have some potentially not at first obvious effects when you have that just because of the structure of the algorithm.
I don't know that the effects are that subtle and complicated. When you have more data, you can learn a more complicated model. And when you learn more complicated model, it can be slower. To speed things up, one thing you could do is you could try scoring on a subset of the data. And if there's a really big, if there's a really strong signal, you don't need a lot of examples to detect that. So you don't necessarily need to look through all instances. So there are many ways you could probably optimize this. Hiram's put some work into optimizing it in different ways, but there's almost certainly more you could do if there were particular domains you cared about and did not work well. At that point in the space, you could say, well, here are the compromises I'll make in order to perform better.
Yes, since you were talking about comparing to like the RBM guys, I wonder, does it make sense to do dropout for SPNs?
Dropout. I don't know of anyone using dropout to learn probabilistic graphical models. There's actually, so.
But this is still kind of a network structure, so it seems like you could at least try it. I don't know if it makes sense or if it works.
So here's what I think dropout in a graphical model, here's where I think it might be useful. I think if you're optimizing something like pseudo likelihood and you wanted to make it, and you wanted to discourage it overfitting to a few strong interactions, and thus ignoring all the other variables, something like dropout might force it to pay attention to other variables. So I think there might be something like dropout that you could use when you're optimizing pseudo likelihood.
But here you could literally like drop out some of the nodes, right? Which would really drop the whole subtree, I guess. But,
yeah, if you think about the equivalence to graphical model, then when you drop out some of the variables, you're basically adding noise that's just going to lower the visual information between variables.
yeah, basically.
So you're going to be making the signal harder to find. Maybe you can come up with something interesting where that helps. I'm not quite seeing it right now. Incidentally, in completely separate work, more related to the adversarial machine learning, working with lead programming, we recently found that actually dropout does help learning support vector machines. Really interesting. That'll be at the perturbation optimization statistics workshop at NIPS in 2 weeks. SPNs or just linear? It works with just linear SPNs. You do the best you can parameters between the L2 penalty, and then you compare it to also adding in dropout, and it works better with dropout, which is on some data sets, also with many variables and some sparse features.
So I guess it's probably just working as a regularizer.
Exactly. Yeah.
Get it down to.
Yeah, and people have shown that this helps on logistical regression.
Yeah, I think that's
Wagner, Wager, Wang, and Yang at the last year, the next paper. And they have some other work in EMLP or ACL on showing how it's also helped with CRF. So yeah, I'm interested in dropout too because I think it's interesting. But that connects actually to a different line of work that's a completely separate topic. You're also going to pizza.
So why don't we begin?
Thank you.
And what I would suggest is, we have pizza here, everybody pick like 5 minutes, grab pizza, and then we can come back and convene and have more discussion and so on. The pizza, at least 2 of them are vegetarian, 3 are vegetarian, 1 Muslim, and so hopefully.